So last time we learned about entropy, and we had just learned how to use entropy to predict whether or not a reaction will occur spontaneously as written at a specific temperature by calculating the entropy of the universe. And the entropy of the universe is the sum of the entropy of the system and the entropy of the surroundings. The entropy of the surroundings we calculated using the opposite of the enthalpy of the reaction, which is just the sum of the standard enthalpy products minus reactants from Appendix 2, divided by the absolute temperature in Kelvin. And the entropy of the system we calculated from the standard entropies of the products minus the reactants. Again, these numbers were all in Appendix 2 at the back of your book. And the second law of thermodynamics said that the entropy of the universe must be increasing. Therefore, if we get a positive delta S of the universe, then the reaction is spontaneous. If we got a negative delta S of the universe, then the reaction is non-spontaneous. What if we get a 0 or close to 0 for delta S of the universe? Then what's the reaction doing? Good, it's at equilibrium. So both the forward and reverse reactions are happening at the same rate. So we stopped right here before we talked about the third law of thermodynamics. So the third law of thermodynamics is still talking about entropy like the second law, but this is now referring to how can you possibly get down to an intrinsic entropy value of 0? And the answer is you can get down to it if you are in a perfect crystalline form, so completely perfectly ordered, and you get all the way down to a temperature of absolute 0. That is the only way to have an entropy value of 0. Now, this is not a change in entropy. Obviously, change in entropy could be 0, and change in entropy could be negative, but the intrinsic entropy value of a substance is always a positive number, because nothing except for a perfect crystalline substance at absolute 0 has 0 disorder. Everything's got a little bit of disorder. If nothing else, the motion of the atoms, the motion of the electrons in the atom, something is moving to cause some amount of chaos that's going to cause there to be some entropy. So that's the third law of thermodynamics. The only possible way to get all the way down to an entropy value of 0 is if you get your temperature all the way down to 0 and you're a perfect crystalline form with no disorder whatsoever. So that was the third law. All right. Let's move on to the next section. So we are now on section 8.5, and we're continuing this idea of predicting spontaneity, and that's what we're going to be doing for the rest of the chapter. The very last thing, again, we did with entropy was calculating the entropy of the universe to predict spontaneity. And now we're going to talk about the third thermodynamic state function. So we've talked about enthalpy in chapter 5, delta H. We've talked about entropy, S. Now we're going to talk about something called Gibbs free energy change, which is the uppercase G. Back in the appendix, when you were looking up those thermodynamic values for delta H and S, there was a third column that said delta G. And so that is what we're going to be talking about now, is the delta G, the column in the middle, and how we use this. So we know that in order for a reaction to be spontaneous, delta S of the universe must be positive. And we know that we can substitute in negative delta H of the system divided by T for delta S of the surroundings, like I have over there. We can solve this down to get to this idea and saying, okay, this has got to be greater than 0. It's got to be positive in order for the reaction to be reacting. We're going to replace this term, negative T delta S of the universe, with a term G. And this G, we're going to call that Gibbs free energy. So this G is going to be Gibbs free energy, named after the scientist who studied it, Gibbs free energy. And just like enthalpy and entropy, it's a state function based on thermodynamic values. Now, Gibbs free energy, the only purpose of it is to predict spontaneity. That's the only time we use it, is when we're predicting whether or not a reaction will occur spontaneously as written, or non-spontaneously, or if you're at equilibrium. So that's the only real reason for it. And here's our first equation for it. Delta G is equal to delta H, our change in enthalpy, minus T, temperature, times delta S. Now, because these are being subtracted, we have to pay attention to the units. What's the rule about things when they subtract in their units? They must be what? Same units. Delta H values, we usually have these in kilojoules per mole. Delta S values, on the other hand, are usually in joules per mole Kelvin. Now, the temperature is going to be in Kelvin, so that'll get rid of the kelvins, but we still have the issue of kilojoules versus joules. So make sure that they are both, generally you're going to move to kilojoules, make sure that they are both in kilojoules before you put them into this equation. All right, here, I'll write that over here. So once we have calculated delta G, how does that tell us if a reaction is spontaneous? And here are the rules. If delta G is less than 0 or negative, the reaction is spontaneous in the forward direction. If delta G is positive, the reaction is non-spontaneous. And just like with delta S, if delta G is 0, you're at equilibrium. However, these two rules are opposite from delta S of the universe. Delta S of the universe was positive for a spontaneous reaction and negative for non-spontaneous. Delta G is the opposite. Delta G is negative for a spontaneous reaction and positive for a non-spontaneous reaction. So be careful you don't mix those up. All right. That issue's still happening. There we go. So this table is on the middle of page 851. 851, and I don't know why it keeps on going black like that. That was the other issue that they couldn't fix. All right, there we go. So this table summarizes what we just said about delta G, but now we're breaking it down into what's happening in the equation for delta G with our enthalpy term and our delta S. So remember, enthalpy. If change in the enthalpy delta H is positive, that means the reaction is what? Endothermic or exothermic? Delta H is positive. Endothermic or exothermic? Way back to chapter 5. If delta H is positive, does that mean it's gaining heat or losing heat? Gaining heat. What do we call that? Endothermic. Whereas if it's negative, it's exothermic. So if delta H is negative, that means we are talking about a exothermic reaction. If it's positive, we're talking about an endothermic reaction. And last time we said that exothermic reactions favor spontaneity but does not guarantee it. So the exothermic reactions up here are where delta H is negative, so this one and this one. It's doing that. Now, delta G will be negative and spontaneous if delta S is positive. So if you have an exothermic reaction coupled with an increase in entropy, then you will always get a negative delta G and you will always end up with a spontaneous reaction. So that's what that first column or first row says. If delta H is negative or exothermic, delta S is positive, so you're increasing the entropy. So we have a negative for delta H and a positive for delta S. That means both of these terms are negative. Delta G will be negative no matter what, and you'll definitely be spontaneous. However, if you are exothermic but you are decreasing your entropy, then which of these terms is bigger will determine whether or not your delta G will stay negative. Because this term will be negative. This term will end up being positive if delta S is negative, because two negatives will cancel out. So if this term ends up being bigger, then you will end up with a positive delta G and it will become non-spontaneous. So that's what it means here by delta G is negative if the T delta S is the smallest term, and that's spontaneous, but it is positive and therefore non-spontaneous if the T delta S is the larger term. So temperature is going to be what's going to have the biggest effect on that, because delta S in kilojoules is usually a very small number. Entropies are much smaller numbers than enthalpies, which is why we usually report them in joules instead of kilojoules. Temperatures in Kelvin, however, are usually very large numbers. For example, room temperature is 298. That's a big number. So the temperature is going to have a bigger impact on that term than the entropy value. And then the opposite is true for an endothermic reaction. If your endothermic or delta H is positive and you are negative, or your entropy is decreasing, then you're always going to be non-spontaneous. If your entropy value is positive, but you're also increasing in entropy, then again, it depends on the temperature. So let's try this out. So a reaction, according to that table, will be spontaneous only at high temperatures if both your delta H and delta S are positive. And I don't know why you were messing this up again, but I don't know. Well, we're on page 851, so let me just write in the values that for some reason are not showing up right here. So for a reaction in which delta H is equal to 199.5, well, that's showing up now. Hello. That's weird. And that got rid of it again. All right. 99.5 kilojoules per mole, and delta S is equal to 476 joules per Kelvin mole. Determine the temperature above which the reaction will become spontaneous. So in this case, they are both positive. So looking at our table here, they're both positive, so we're down here in the bottom. So for it to be spontaneous, T delta S has to be greater than delta H. So that's what we need. We need T delta S to be greater than delta H. So before we can compare these, we need them to both be in the same unit. So we need them either both be in kilojoules or both be in joules. So we went ahead and took delta S and turned that into kilojoules so we can compare. So there's our delta S term. Here is 0.476 kilojoules per Kelvin mole. Delta H again is 199.5. So what T term, or what do we end up with for the temperature there? Good. We end up with 419.1 is the temperature, the minimum temperature. So T must be greater than that. Make some space here. And 419. Now what unit is this going to be in? Kelvin. That's in Kelvin because of that. That's in Kelvin right there. What unit are we asked for it though? Celsius. We're asked in Celsius. So what's our last step with this? How do we convert Kelvin to Celsius? Good. Minus 273. So that gives us what in Celsius? 146 degrees Celsius. And that's your answer. The minimum temperature to make this reaction spontaneous is 146 degrees Celsius. So going off of that table, I could have given you any combination, but I probably will not give you a combination that is always spontaneous. So I probably would give you one of the either when they're both negative or they're both positive, and then asked you for at what temperature it becomes spontaneous. Questions about how to do that one? All right. So I mentioned that there were values for this Gibbs free energy in the appendix right next to our standard enthalpies of formation and our standard entropies. And those are our standard free energies of reaction, or of formation, just like standard enthalpies of formation, same idea. So you can calculate the standard free energy of the reaction in the exact same way by taking the sum, go to the equation, by taking the sum of the products minus the sum of the reactants, which is the exact same way we calculated over here our standard enthalpy of the system and our standard entropy of the system. Exact same thing. Where delta G, standard formation, is the standard free energy of formation. Now, I wanted to pause and talk about the term standard there. We always know it's standard when we see this little degree symbol. And we saw that back in chapter 5 when we were talking about standard enthalpy of formation. And we saw it again when we were talking about the standard entropy of a substance. And we just keep on saying the word standard. But what does standard mean? So I'll take back real quick, and this is on page 852. What do I mean by standard state? Well, if it's a gas, then pressure is important. So that means the gas is at 1 atmosphere of pressure. If it's a liquid, it's a pure liquid. If it's a solid, it's a pure solid. Elements are in their most stable allotropic form at 1 atmosphere and 25 degrees Celsius. If you are a solution, so you're aqueous, you are 1 molar, so 1 m concentration. Why am I pointing this out? Because in a little bit we'll say, well, what if we're not at standard state and mess with one of these? Now we know 25 degrees Celsius, we know how to change that up because that's in our delta G term, our temperature, but how will these terms change if we say change the concentration, we're no longer 1 molar, or for gas, change the pressure, we're no longer 1 atmosphere. So I'm just pointing out that this is what those values in the appendix mean when they say standard state. So later when we say we're non-standard state, you'll know what is important that we have changed. So the big ones to pay attention to there is if you're a gas, 1 atmosphere pressure, if you're aqueous, 1 molar concentration, and of course the temperature 25 degrees Celsius. All right. So if I wanted to find the standard Gibbs free energy of a reaction, I would just add up the products minus the reactants, looking up the values in the back of the book. So for example, here, for the reaction to make carbon dioxide from its elements in their standard states, that's carbon graphite, that's the most stable allotropic form, not diamond. And oxygen is O2, it's a diatomic in a gas form. So the standard Gibbs free energy of formation for carbon dioxide is the delta G of this reaction here, making the compound from its elements in their standard states. This is exactly the same thing we did back in chapter 5 with delta H, just plug in a G for H, and it's the exact same work. All right. Again, why is it messing up here? So that's methane in what form? Gas? This is supposed to be a gas. Calculate the standard free energy changes for the following reactions at 25 degrees Celsius. So if we have methane, CH4, plus 2 oxygens goes to carbon dioxide and water, 2 waters. Now, it's just going to be the sum of the products minus the sum of the reactants. So for A, the standard, no, I'm writing H, standard G standard for the reaction would be the standard, stop writing H, G of our first product, which is carbon dioxide gas, plus our second product, formation, standard G formation of water in the liquid form, not in the gas form. What do I do with that term for water, though? When I plug it into this equation, what do I need to do with water that I didn't have to do for carbon dioxide? Good. There's a 2 here, so I need to multiply that Gibbs free energy term by 2. Everybody see why we had to do that? So there's our products minus now our reactants. So we have the methane. And same as with the H2O, 2 times the standard Gibbs free energy of oxygen gas, O2 gas. Now, normally you would look up these values in the appendix. They've already listed them for us there. So for CO2, it is negative 394.4. For H2O in the liquid form, it is negative 237.2. Make sure when you're looking at the appendix, you're careful with states of matter, since H2O is listed in both gas and liquid form. For methane, it's negative 50.8. Now, why did they not bother to list what the value is for O2? If this is the Gibbs free energy for the formation of the compound from its elements in their standard states, why did they not bother telling you what that value would be for oxygen, O2? It's already an element at standard state, so what is its Gibbs free energy of formation? 0. Good. So that's why they didn't bother. That term right there is just going to go down to 0 because it's already an element in its standard state, just like we had back in Chapter 5 for the standard enthalpies of formation. Plug in the values and solve, and we get negative 818 kilojoules per mole for that first reaction. Any questions about how to do that? I don't think we really need to do B. It's the same idea. So, is this reaction spontaneous as written at standard state conditions? Yes, because delta G is negative. So it is spontaneous as written at standard state conditions. May not be spontaneous if you change the pressure, because these are gases, or at least the reactants are gases. And it may not be spontaneous if you change the temperature, but it's spontaneous at standard state conditions at least. So, all right. Let's talk about, well, what if you're not at standard state conditions? Well, why might you be concerned about not being at standard state conditions? What if you had, why is this important? Do you even care if a reaction is spontaneous? Well, what if you had a reaction that you really need to run for some industrial reason, but it's not a spontaneous process at, say, standard conditions? For example, here is calcium carbonate. What's the common name for calcium carbonate? What do we commonly use it for? What? That's calcium bicarbonate, close. Baking soda is calcium bicarbonate. Calcium carbonate used to be significantly more common in schoolhouses, but not so much these days now that we have whiteboards. Chalk, yeah, that's chalk. So calcium carbonate can decompose in an equilibrium reaction to make calcium oxide, and then carbon dioxide is a byproduct. Calcium oxide is called quicklime, and it's a very important material, just like ammonia, and when we were talking about equilibrium, was a very important material that we needed to fix nitrogen and make fertilizer and all the other stuff. And we learned about Haber, the mad scientist who killed people. But same idea here. We really need calcium oxide, and it is used as water treatments. It's used in scrubbing, air scrubbers, that kind of thing. So it's a very important industrial compound. And it's very easy to make from calcium carbonate, which is very abundant and very cheap. The problem is this reaction here, if I find, so delta H and delta S, so what we're trying to find here is whether or not this is spontaneous, we'll end up with a delta G value of 130.0 kilojoules per mole. So is this reaction spontaneous under standard state conditions? No. So under standard state conditions, this reaction is not going to occur. Chalk isn't just going to turn into calcium oxide on its own. But if I am in the industry and I need to make it, I need to figure out, well, what conditions do I need to change to make this spontaneous so I can make the quicklime, I can make the calcium oxide. So I need to find a temperature that will give me the product I want. So in this case, I'm going to, God, why is this still messing up? Yeah, 0. Yeah. 0 is where you switch from being positive to negative. So again, we're going back to the idea of what's the minimum temperature we need to make this reaction spontaneous. So we're going to set 0 equal in for delta G, and set that equal to the delta H minus T delta S. Solve for which temperature. So this is just like the same problem we did a couple minutes ago. And we find that a temperature of 1,108 Kelvin, or 835 degrees Celsius, is the minimum temperature it takes to get this reaction going forward spontaneously. So we know that if I'm manufacturing calcium oxide, that is the minimum temperature I need my reactor to be at to get this to start turning, favoring products. Now I'm probably going to go hotter than that, so I drive the reaction a little bit more forward, but this is the minimum temperature it's going to take to start favoring the products and making the calcium oxide. All right. We could also do this for a physical reaction and use this to predict the entropy associated with a physical change. So we talked qualitatively earlier last time about the entropy associated with phase changes. So melting, going from a solid to a liquid, was that a positive or negative change in entropy? If I'm going from a solid to a liquid, did I increase my entropy or decrease it? Increase it. But now, using this idea, what did I just hit? Where? Yeah, right there. Now I can actually calculate exactly what the entropy change is, because I know for water what its melting point is. What is the melting point for water? What's the melting temperature? The temperature at which water starts to melt? 0 degrees Celsius, which is what Kelvin? 273 Kelvin. So I'm going to take this equation and I'm going to plug in for temperature. I'm going to plug in 273. And we can calculate what the delta H is for the phase change of ice melting into water. And it's 6 in joules, because we want them to be in the unit of joules. It's 6,010 joules per mole. And so we can calculate the entropy value of melting. Now, if we reverse this, we're still at a temperature change of 273, because 0 is not just the melting point, it is also the freezing point. And at that temperature, technically melting and freezing are at equilibrium. So that's why delta G is 0 at the melting point. So we can also use this equation to calculate the melting point of a substance we may not know the melting point of, if we know what their entropy and enthalpy values are. So a negative delta H value is because when you are freezing water, you are no longer endothermic, you're now exothermic. So that's why it's the same number, you just ended up with a negative delta S, because going from liquid to solid is decreasing your entropy. We would expect a negative delta S. So we can use this to estimate what the enthalpy will be for a phase change. Let's go ahead and try that out. So I'm on page 855, sample problem 18.7. The molar heats of fusion and vaporization of benzene, so this is your delta H, so they mean by molar heat of fusion and vaporization, that's delta H values, are 10.9 and 31.0 kilojoules per mole respectively. Calculate the entropy changes for these two phase changes, the solid to liquid or melting, that's what they mean by fusion, that's melting, and the liquid to vapor transitions or boiling for benzene, given that one atmosphere of pressure, benzene melts at 5.5 degrees Celsius and freezes and boils at 80.1 degrees Celsius. Now they've already gone ahead down here and calculated those in Kelvin for us because we're going to need them in Kelvin. So we're going to do the same thing that we just did for water. At the freezing point or melting point or the boiling point, vaporization point, whichever phase change, your delta G is always going to be 0, so we can use this form here. Delta S is equal to delta H over the temperature, and use that to solve for our delta S's. So let's do the melting first. So delta S is equal to delta H over the temperature. Now, when we were using these delta H's, we made them in units of joules because delta S is reported in units of joules. But they're typically given to you for an enthalpy value in kilojoules. And sure enough, yeah, we gave it to you in kilojoules. So 10.9 kilojoules, how many joules is that? You can convert at the beginning or the end. It doesn't really matter when. I'll just go ahead and convert at the beginning. 10.9 kilojoules is how many joules? Good. 0.0109 joules per mole. So that's what goes in for our enthalpy term. 0.0109 joules per mole, and then divide, this is the freezing or fusion, so that was 278.7 Kelvin. Oh, you're right. That should be getting bigger, not smaller. Sorry. I'm very gullible while I'm up here. Sure, that sounds like a good answer. That should be 10,090. 900, right? 1, 2, 3, yeah. 10,900. Okay, that looks better. I'm like, wow, am I getting such a small number? 10,900 joules per mole. All right, so 10,900 divided by 278.7 gives us how many joules per mole Kelvin? Getting 39.1? And that is our delta S of fusion. It's 39.1. So go ahead on your own and find out what the delta S of vaporization is here. So the boiling point is 353.3 Kelvin, and the delta H of vaporization is 31.0 kilojoules per mole. What did we get? Good, 87.7. 87.7 joules per Kelvin. How are we feeling about that? All right, only one more section of calculations for this chapter. All right. So the last section that involves calculations is now free energy change and equilibrium. All right, so before we get into this, I want to just remind you of some terms from the equilibrium chapter, which was chapter 15, before we forget what that is. All right, so what is uppercase K? Chapter 15, and hey, actually we continue to use K in 16 and 17, which you just took a test on. It's a constant. How do we calculate K? Is equal to what over what? Good. Products over reactants. And these could be in what or what? Is this grams, moles? What is this? Molarity, concentration. So this is concentration in either molarity or concentration of a gas is in what? Pressure. So these are either concentrations or pressures. Concentrations in molarity or pressures in what unit did we use? Atmospheres, right? Good. So that was the equilibrium constant K. What was Q? Quotient. Not equilibrium, but just because you may not be at equilibrium, we just call this the reaction quotient. Reaction quotient. So K was the equilibrium constant for when you were at equilibrium. Why is it doing so many lines there? Equilibrium. And Q is the reaction quotient. How do we calculate Q? Still products over reactants. It's calculated the exact same way. So what is the difference? Wow. You may not be at equilibrium. So if Q and K are the same thing, then you're at equilibrium, but it may not be. All right, but it's still calculated the same way. But we used this back in chapter 15 to predict whether or not we were at equilibrium, and if not, which way the reaction would run to get to equilibrium. If it was needing to run forward to get to equilibrium, if Q was too small, if Q was too big, then it would need to run backwards to get to equilibrium. So that's what we learned about in chapter 15. So keeping on to that idea, let's go ahead and try out a problem, which for some reason is not on the slide, but if you're following along on page 856, it describes the problem here. So the question is, we have a reaction of hydrogen and iodide to make HI. Right here is our reaction here. So they're all gases. And we want to know whether or not we're at equilibrium, or if we're going to happen this spontaneously, what's going on here. And we're given starting partial pressures of these, and I'm starting at the partial pressure of HI of 3 atmospheres and a starting partial pressure of H2 of 4 atmospheres. Why am I not given a starting pressure of I2 though? It's a solid, so does a solid even show up in a reaction quotient? No, so we're going to just ignore iodide. So if I calculate Q, the reaction quotient in terms of pressure, why did I square hydrogen iodide? Good, the stoichiometry comes into effect. There's 2 hydrogen iodides, so it got squared. So it's the pressure of hydrogen iodide squared, so 3 squared, over the pressure of hydrogen, your reactant, 4. So we end up with Q being equal to 2.25. So here's our equation that relates delta G non-standard, I don't know why it's not showing up, delta G non-standard is equal to delta G standard plus RT natural log of Q. This is equation 18.13. Let me just write it over. I think it's a good marker. Delta G is equal to the standard delta G. So if this was standard, what would these pressures be? For delta G standard, what would be the pressures? 1 atmosphere. Good. So we know we're not standard state because these are not 1 atmospheres. These are higher pressures. Plus R, gas law constant, T, absolute temperature, temperature in Kelvin, times the natural log of Q, where Q is your reaction quotient. So if we plug all of this in, and 2.6 kilojoules was the delta G, right here, delta G standard that we got from adding up products minus reactants in the appendix, and then we went ahead and did that for you to save you some time. We get a delta G non-standard of 4.3. So does this reaction occur spontaneously at these pressures? If delta G is 4.3, is that a spontaneous reaction or not? No. Good. Delta G is positive, so it's non-spontaneous. So at these pressures, it is not spontaneous. Let's see what happens. Again, say this is an industrial process that I really need to happen. I really need to make this hydrogen iodine gas. And instead of changing the temperatures, I'm going to change the pressures to try and make this reaction spontaneous. So I could solve for Q, where we get spontaneous. In this case, I think they just went ahead and changed the final concentration of hydrogen iodide to 1 atmosphere. Oh, didn't show it here. But if you're following along in the textbook, on the top of page 857, they changed this pressure from 3 to 1 atmosphere. So now this term became 1, and you ended up with a negative delta G, which meant it was spontaneous, and that's on the top of page 857. So by changing around your pressures, you can get the reaction spontaneous, just like in the last section we changed around the temperatures to get the reaction spontaneous. So let's try an example of this. The equilibrium constant Kp for the following reaction, N2O, goes to 2NO2, is, I don't know why that P is big, is 0.113 at 298, which corresponds to a standard free energy change, or delta G standard, of 5.4 kilojoules per mole. In a certain experiment, the initial pressures of NO4 is equal to 0.453 atmospheres, and NO2 is equal to 0.122 atmospheres. Calculate what delta G, notice there's no degree, so this is non-standard, for the reaction of these pressures and predict the direction in which the reaction will proceed spontaneously to establish equilibrium. So is it going to run forward or backward? Now, in this case, do we need this value Kp to solve this problem? Is Kp anywhere in our formula for delta G non-standard? No. So this was kind of like giving you information. This is a kind of not really too small K. This is a relatively medium-sized K, which means that you're going to end up with, in general, a mixture of reactants and products. So we're trying to figure out if we change these pressures, whether or not it's going to be spontaneous forward, or we're going to have to go backwards to get back to equilibrium here. But that 0.113 value is actually not used in our calculation. It's kind of just this FYI stuff. So I hear a lot from students, they get confused about why am I given these numbers if it doesn't go into the calculation. And that's a big part of just in general, when you're going out in your job and your career, you're going to get a lot of data, and filtering out what data do I need to solve the problem and what I don't need is a big part of that. So be careful. Delta G, our equation for delta G non-standard, does not have K in it. So don't just try and stick that number in there randomly. I see that a lot in students' work where they just try to stick in any number they see in the problem. Break down what numbers do I need. So for this problem, to calculate delta G, I need delta G standard and the temperature and Q. I'm given delta G standard. I'm given, well, I'm not given Q, but I'm given the pressures. I can use that to find Q. And then I'm also told what the temperature is, 298 Kelvin. So I have everything I need to plug into this equation and solve for delta G. So delta G non-standard is equal to delta G standard plus RT natural log of Q. Plug all those values in. Delta G standard plus RT natural log Q, where Q is, again, products over reactants. Plug in those pressures, and there's our Q. And we end up with a delta G non-standard of negative 3.1. So if delta G is negative, then the reaction is spontaneously going which way? Forward or backward? Is the reaction spontaneous as written or not spontaneous? If delta G is negative.
It's spontaneous. It's negative.
Good. If delta G is negative, that means it's spontaneous as written. As written means what? Going forward or backwards? Forward. So the reaction will proceed in the forward direction, or from left to right, to reach equilibrium. All right. What about if we are at equilibrium? Let's say we are at equilibrium. At equilibrium, what will our delta G term be? 0. And at equilibrium, Q is equal to what? K. So hey, look, we just made our next equation. So our next equation says at equilibrium, delta G is 0. So we can use this, just take delta G, or take the RT natural log K to the other side, make it negative, and here's our relationship between delta G standard and K. We can use this to calculate the K of a reaction using this idea. Delta G standard is equal to negative RT natural log of K. So recap of what K can tell us once we have determined K. Back in chapter 15, if K was very big, did that mean the reaction favored the reactants or the products? Did it favor staying as a reactant or favored staying as or going to the products if K is very big? Products, that means it's mostly products. Because remember, K is products over reactants, so a big number means the numerator, the products are very big. If K is very small, that means that the reaction favors what? Going forward or backwards? Backwards. So very small K means the denominator, which is the reactants, is the bigger number. K somewhere in between means you end up with a mixture of reactants and products. So that's what we learned about in chapter 15, and this is, I think, basically the same table. Yeah, it's pretty much the same table. If K is greater than 1, when we take the natural log of it, which goes into that equation, we'll get a positive natural log. If we get a positive natural log, then delta G will stay negative. So we're looking at this equation here. Why? Now I can write on it, but everything else is messing up so bad. All right. So if K is negative, the natural log of the negative number is positive. So if this number is positive, then the whole thing stays negative. Delta G is negative, you're spontaneous. If K, however, is positive, the natural log of a positive number is negative. Negative times a negative will make delta G what? Positive, which means the reaction is what? Spontaneous or non-spontaneous? Non-spontaneous. If K is equal to 1, what is the natural log of 1? What's the natural log of 1? Plug in your calculator if you're not sure. 0. Natural log of 0 is, or natural log of 1 is 0. So if this term goes to 0, what happens to delta G? Everything goes to 0. If delta G is 0, then you're not spontaneous or non-spontaneous, you're what? at equilibrium. So that's where these terms in this table, come on, stupid table. All right. If K is equal to 1, that's why neither reactants nor products are favored and you're at equilibrium. Phew. Let's try an example of this. Using data from Appendix 2, calculate what the equilibrium constant is for the following reaction at 25 degrees Celsius. So our equation here is delta G standard is equal to negative RT natural log of K. That's the relationship between equilibrium constant K and delta G. So which one of these terms can I calculate from Appendix 2? R is just a constant. T is the temperature. I'm told the temperature is 25 degrees Celsius, which is 298 Kelvin. I'm being asked to solve for K. You're not going to find any K's in the appendix. So what is it we need from the appendix? Delta G. Good. So delta G standard, we can get those values of delta G formation in the appendix. Sum of products minus sum of reactants. Let's go ahead and just, in the sake of time, use their number. That's where this came from, the sum of the products minus the sum of the reactants. And we get a delta G value of 474.4. Let's go ahead and divide by that negative RT. So R, and this is in kilojoules per mole. What is R? Gas law constant. What is that? 3.14. What is the unit there? Is that 8.314? 8.314. And what's the unit? What per mole? Joules per mole, Kelvin. If this top term is in kilojoules, what do you think we're going to need to do with that R? Change it to kilojoules as well. We've been doing that one since chapter 11 with the Clausius-Clapeyron equation. So we're going to take that 8.314 and make it in kilojoules, or just say 8.314 times 10 to the negative third, and now we're in kilojoules per mole Kelvin. Negative RT, and then the temperature is 25 degrees Celsius or 298 Kelvin. I can write straight. Is equal to natural log of K. Now, can you have a unit inside of a natural log or coming out of a natural log? No. So we need to make sure all of our units canceled. Did they all cancel? On the left-hand side there? Yeah, kilojoules canceled with kilojoules, moles canceled with moles, Kelvin canceled with Kelvin. No units left. Good. We don't want any units. So what do we get for that whole left-hand side? It'll be a negative number. Good. Negative 191.5. So that's the natural log of K. So how do I find K? E. Lowercase e to both sides. Take the inverse. So E to the negative 191.5 gives you what? Good. 6.95 times 10 to the negative 84. We're going to round to just 7 because of the rules of rounding with natural logs and exponents say that the number of significant figures that goes into the natural log is equal to the number of decimal places that come out of the natural log. So if we're doing the opposite, the number of decimal places that goes into the natural log gave us the number of significant figures coming out of the inverse natural log. or E. So that's why we rounded to just 1. So looking at that for K, if that is equal to K, what does that tell us about this reaction? K is really small, so what does it tell us about the reaction? It's mostly what? Reactants, products, or mixture of both? Reactants. The reaction does not occur in the forward direction very much at all. This is a very small K. All right. So we've been learning so much about whether or not a reaction occurs spontaneously, and I gave the example of this could be very important for an industrial process to try and force a reaction to be spontaneous so that we can get whatever product we're looking for. But for many of you, you may not be going into the industry, so why on earth do you care about whether or not chemical reactions are spontaneous? And here is the issue here. I'm skipping that last problem because we're not doing one like that. The reason is because you are what's called a living system. Most biochemical reactions required for life, whether it's human life or plant life or microbiology life, little tiny microbes or anything, plankton, most of these chemical reactions that create life and keep us alive are non-spontaneous reactions, meaning they will not occur on their own. Life will not occur on its own. So why on earth are we even alive? How do we do this? We can't just do what we did with the calcium carbonate and jack up the temperature to 800 degrees Celsius. That wouldn't work out very well for us. So how do we do this? We do this through something called coupled reactions. Coupled reactions is where you pair a very, very spontaneous reaction with a reaction that is not so spontaneous and use it to drive the non-spontaneous reaction. So how many of you guys have had either biology or A&P or currently are in it? So you probably have already learned about a lot of these reactions. You've learned about the ATP cycle, the Krebs cycle, calcium transport chain, all of that stuff. So I'm not a biologist. I'm not an A&P person. I'm not an expert on this, so I found a lovely video for you by somebody who is an expert on this to talk about all of these equations. And that should